being here. Happy Friday, everyone. I'm not sure where you are, mostly in the Northern Hemisphere, so that will be your summer. So thanks for that. I hope that you're enjoying, I'm not sure your vacation, but at least the weather. Yeah, I'm here right in Ecuador. It's very, it's a lot of fog here and 12 degrees. So it's very cold for us here. It's like 65, which is
Oh.
very unusual.
Ooh.
So, yeah. So let's start. Let's start. And maybe if you can help me, James, and with all the people that are coming, that would be great.
Certainly. Yeah.
Yeah, yeah. So let's talk about quantitative risk analysis today, right? That's what we're going to do today. We're going to record this session, and the ones of and thanks for all for coming, because you're going to have access to it. Otherwise, we don't make it public. So you will have access to it in case you want to rehearse or come back to it for any reason, right? So a little bit. Normally, what I do in these sessions, if you like to share your contact details in the chat, that would be great. If you want to generate a community, as we know that this is a niche, right? And sometimes a niche of a niche. So sometimes it's really good to have people like yourselves talking to each other. Please make sure that you do it. And if you like, feel free to use the chat for that matter. It does for us. It's perfect because it creates this sense of community. I see some familiar faces too, so thank you, David, for coming. I see David, Ash for coming, John, Fritz, a lot of people that we know, and then it's every time that you come, you're in a new family now, right? In this Fairfield Group family that we would like to have. So thanks all for coming. A little bit about me, as Jameson said, this is my 16th year doing QRA. I used to work in Palisade, the makers of at risk, for 12 years, and then the company was sold. So I moved on and I'm working with the Fairfield Group since the beginning of 2024. So it's going to be my second year. Very happy to be here and doing what I like the most, which is QRA and teaching people how to do this quantitative risk analysis and how to introduce yourself to this world of simulation and estimations and ranges, right? Now, what is it that we're going to see today? Today, we're going to take a look to what a risk definition is, right? And we're going to do some of a statistics refresher. We're going to take a look to what Monte Carlo Simulation is. If you're not acquainted to it, remember that this was an introduction. Best practices for integrating QRA and some tools that you can have, plus some conclusions. Right. Main objective today, and this is hopefully what I want you to take home, is to understand quantitative risk analysis. We're not going to be experts at the end of the day, but we're going to understand it, right? That's the main idea, right? That we can understand and we can generate a decent first analysis, taking into consideration aspects of probability, aspects of statistics, selection of distributions, etc., that you can run a Monte Carlo simulation. We're going to use a tool to showcase all this knowledge, but you can use your own. You can even use Excel, or you can even use tools that are free that you can use on the web, even without installing anything. And finally, interpretation of results. Why is it that, and this is mostly the case of people coming here, why is it that you want to interpret results? Because you want to do some things like this, right? You're giving a report that somebody did, right? And this report looks like this, right? So this is what is this telling me, right? Perhaps you've been in this position where you receive a report like that, and you say, well, what is this telling me? Is this good? Is this bad? I have a mean of 5.2 million, which is around here, right? I have a P80 of 5.5 million. So this is good, this is bad. Should I take care of that? What should I do with this? Right? Same thing here. Let's talk date, not let's talk only cost. So I had a target value of September the 26th in 2018, right? And my P80 is October the 30th. So is this good? What does that mean? What is this telling me? So the main idea of today is that at the end of the day, at the end of maybe, let's say in an hour, we are going to be able to answer it, right? So thanks again to every everybody who's coming, much appreciated, right? Now, why is it that we need QRA? QRA is needed because of this, and this is our perspective. Of course, it's you're in sometimes more close to to your industry, and I did it mostly for the take into consideration project, is because average cost overrun for construction projects from 15 to 28%. Large projects take 20% longer than expected. We're talking about big projects, right? So it's, I mean, it could be 2 months that are going to take perhaps one additional week, but it could be 20 months, and it could be additional 4 months that you have to pay 4 months of salaries additional, right? 91% of the projects go over budget, over schedule, or both, right? And here you have all the sources, and this is why we are here, right? Because we want everybody to be aware of this, right? That even though we get certified, we get prepared, etc., the technologies evolve. We have new people, new crews, new regions, new technologies, etc. So we are still not yet there, right? And what are the main reasons for the delays, right? Because that's the diagnostic. We know that we are late. We know that we have a lot of additional costs. Why? Mostly because we have sometimes initial planning. It's not good. We have scope creeping. Of course, please don't be a scope creeper, right? We have inadequate communication, ineffective project management practices, poor change management. This is a key one, right? Technological challenges, right? With all this new wave of new technologies everywhere, right? What happens is that these are not, I mean, we shorten the testing time of everything. We like everything to be done quickly as much as possible. And sometimes we're not yet there. External factors, like, of course, we all know what's happening in the world. So we have a lot of economic stability, right? And a lot of uncertainty. We don't know what's going to happen. We really don't know what's going to happen tomorrow. We don't know. So that's why today we're going to focus here, right? This is our little grain of sand that we're going to add or try to add value to the practice by improving our risk management capabilities. That's the main reason why we are here, right? Now, why is it that we need QRA? Now that we know that we have these deviations in cost and time, because we want to improve. Now that I'm going to go a little bit deeper in this first step, right? Because we want to improve, right, our static scenarios, which are out of reality, right? The static scenarios normally they are typically, right? We have scenarios, we have the optimistic, pessimistic, and average, right? Like this. So the optimistic, they take into consideration that everything is going to be positive. Inflation is going to be low, raw materials are going to be stable, no accidents, no rotation, everybody's happy with the project, right? Which is totally untrue, right? And then at the same time, right, we have, I'm so sorry, I hear some noise over there. But if you have your mic on, if you can turn it up, that would be great. So that's one. But then if you go to the pessimistic one, remember that we have a second box here. The pessimistic one, everything is bad, right? You have high inflation, you have instability in prices, you have high prices in raw materials, low productivity, etc. Right? So I wouldn't say exaggerate, but you consider this that you're going to have the perfect storm. And then we have a last one, which is the average of everything, right? You have it like this, and it's the average of everything. Now, my concern with that is that these are static scenarios. These are not things that are going to happen ever, because they consider that variables are going to stay the same for the rest of the project. They are not moving simultaneously, right? And we have to take that into consideration, that the variables move simultaneously, right? And we're not taking that into consideration, right? Because these are static scenarios. So this is what we do. So this is our methodology, and this is the evolution, let's say, to a dynamic model. So the static models can be easily improved adding uncertainty, right? Uncertainty could be that, for example, you know that the tasks you're going to take 10 to 20 days to do it, but in the first model, you would say, well, if it takes from 20 to 20, I will do in 15, because you always take the average. But in this case, what you could do, you can say, well, if a task is going to take from 10 to 20 days, So I can do it like this, right? I can generate a range. And this is the key word here, and this is how I like it to be, right? Is that you have ranges. And now that you're thinking in ranges, everything changes, right? Everything improves. Why? Because before you had a 15 as the given number for the task, but now you know that it takes from 10 to 20 days. The moment that you have that, maybe you didn't know, but there's a probabilistic distribution called the uniform distribution that looks exactly like this, right? Where every number from 10 to 20, they have the exact same probability of happening. So you can easily set it up like this and say, well, the uniform distribution can be like this, right? Now, what happens if you have more information about the range, and the range goes like this? You have 10 and 20, right? These are your boundaries, but you know that most likely you're going to be in the range of the 17. So what happens is that besides having a potential uniform distribution, this could be also a triangular distribution. It could look like this. So instead of, you see that this knowledge, you've already had it. And you as a project manager, or you in any of the, I would say, teams that you have in your model, in your project, you already have this knowledge. So when you already have this knowledge, it's very easy to think in ranges. And these ranges are going to be translated into uncertainty through the use of probabilistic distributions. Every probabilistic distribution, as you will remember, will have parameters, right? Like for example, here, the uniform distribution that I use will have a minimum of 10 and a maximum of 20, right? Like this. If you have a triangular distribution like the one that I showed you before, it's going to have a minimum of 10, a most likely or a mode of 17, and a maximum of 20, right? Every distribution is going to have different parameters. And that's the key part of it. The software that we're going to use, and any software that does Monte Carlo simulation, is going to receive parameters and distribution types. Now, the good news is that for you to enter the quantitative risk analysis world using Monte Carlo, you will need no more than 3 or 4 distributions. With that, we're done. If you manage to dominate that, maybe in the first 3 or 5 months, right, then you can go and improve the use and the selection of the distributions. But with 3 or 4 distributions, you're done. You're more than ready to do it. Now, we don't want to be like this poor guy, right? This risk manager that didn't calculate, that is using only qualitative analysis. And he's saying, right, there's too much risk and I don't know where to move. Should I go back? Should I move forward, right? It's paralyzed. Why? Because he doesn't know his boundaries. We should know the boundaries. That's what we need to do. As if we know the boundaries, right, we can move. We know that, for example, if you have a business that is a manufacturing facility, so you should know the boundaries. You should know the throughput of the machineries. You should know what is the probability of breaking it down, what are the contingencies, etc., etc. You should be prepared, right? That's the size or the fluffiness, if you like, of the pillow that you'll sleep with every night. If you don't have that prepared, of course, you're going to have a bad time every day. You're going to hate your job because you don't know your boundaries. You don't know what can happen. But if you have thought about this, if you calculated the risk of your operations, right, that's totally different. Let's say that you work in a financial model. You work in hedging funds. You work doing financial instruments. Normally, this industry, we're lucky with this industry because they have a lot of information and they know how to calculate the boundaries. The same for the insurance industry. But if you're in the construction industry, that's totally different. That's a different game. And that's the main idea here, that you will be able to calculate these risks using this simple formula, right? The risks are just going to be a function of the probability of the risk happening and the consequence of the risk happening, right? The probability, as with any probability, it will go from 0 to 100%, right? This is what will happen with the probability. The consequence could be in time, for example, days, or it could be in cost, dollars, euros, pounds, anything, right? So the main idea here is that you will have to profile, you will have to calculate and translate every risk that right now maybe you have as qualitative to quantitative. That's the main idea. When you do that well, this is very, very straightforward and very easy to set up. Now, if we go to disaggregate risks, you're going to see that we have two types of risks, and I like it to be like this, and the majority of software treat them like that, right? We have one type of risk, which is the uncertainty. And this uncertainty has a probability of 100%. That means that it will happen. Whatever it takes, it will happen. You cannot do anything to prevent that from happening. And this is due to the natural oscillation of variables, right? That's what happens. You have natural oscillation of variables. And when you have this natural oscillation, what happens is that, for example, you say how many, I don't know, square meters you paint per day. You have a crew, they are painting a building, and I'm not an expert of this, of course. I will say you paint an average of 25 square meters per day. That could be totally absurd, or maybe this is right on. I really don't know. But the next day, you did 25, right? Next day you do 28, because now the parts are easy to reach, right? But then you go to the corners and there are some safety issues. So maybe you do 14, and the other day you do 20, and then again you do 25, and it's a Friday, then you do 20 because you just want to leave. And then again, next week is 24, 25, 20, no weird corners or reaches, then you do 19, then it's a Friday, you do 15 or 16, etc. There was no accident here. There was no bad weather, no winds, anything like that. You just had productivity in place. Let's say that you have homogeneous crews doing the same, but of course it's not going to be exactly the same every day. So you can say that you will have between 20, 25, and 27 square meters per day painted. So this is going to be your distribution, right? Like this, 20 to 25, like this, right? Or you can say it's going to be between 20, 22, and 27. So this is going to be optimistic, right? Because the weight of the distribution is going to be on a higher range. And the other one is going to be more pessimistic. Why? Because the center of mass of the distribution, the bias of the distribution is going to be towards less painted square meters, right? And this is how we should see it. So now that we have that in place, what we could do is we can set up our own distributions. That's the main idea, right? So this is due to the oscillation of variables, right? So always remember, it's like painting a wall is like the time that you do if you commute, of course, between your home and your office. With 70 minutes, 19, 20. I'm very lucky. I live in a city where I do no traffic. I do it in 6 minutes. With traffic, I do it in 12 minutes. So if it's a very, very nice city, and if it's very bad traffic, I will do it in 20. So if you live in a big city like I imagine you guys do, so perhaps your numbers are twice or three times as much. Now, then you have your risk events, and these are discrete risks or discrete events that could occur or not, where the probability is going to be between 0 and 1. So maybe we have a risk of, for example, malfunction of security system, right? You're painting the building, and then, oh, you cannot go there because there's a malfunction of the security system. There was a 5% probability of this happening, but if this happens, perhaps your number of meters that you painted goes from 25. Remember that we have here 25, maybe to 3, because they took all day to fix it. So the productivity goes down, right? So you have this discrete risk. So what happened is that at the end, the delay that this had, right, was 22 days, right? My delay was 22 days. That was the impact. That was the consequence of my risk. And that's how you see it. What happens in the example where you go home, right, from office to home, there's an accident in the middle of the road, or there's a traffic, there's police checking the licenses. Oh my, you have so many things. Then suddenly a 20-minute trip could be 60 or 80 minutes, right? Because you didn't know, you didn't prevent for it, you didn't have a contingency plan. You just have to wait until your turn comes and then go, right? So these are the two differences that we make between the uncertainty and the risk events. And as long as we are aware of that, we just have to have one very important premise, is that we don't have to duplicate, right? That means that if you add a risk event on top of an uncertainty that you already added, you're over allocating risk. If you over allocate risk, you're going to maybe lock resources or your resources for some activities that are never going to happen, or for a level of contingency that's never going to happen because you're too conservative. Now, if you're in the risky side, maybe you say, no, I'm never going to duplicate. This event here, the accidents in the middle of the road, no, they never happen because it's the summer, nobody goes in the streets. Don't you worry, I'm not going to take that. So you're under allocating risk. If you under allocate risk, the moment that it happens, you don't have the money to be prepared to do anything with that. You don't have money for the contingency plan, you cannot mitigate it, etc. So these are the two elements that we're going to use in a risk framework, right? The typical models, we're going to see today a cost estimation model, but it could be a project schedule, portfolio management, an NPV calculation, operational risk, statistical process controls, etc. So in a nutshell, and before I go to the model and show it to you, is that remember how this comes, right? You have a model logic, which you have here, this model logic, and then you have different variables here. If you have an NPV model, this could be your sales cost, variable cost, fixed cost. If this is an estimation model, this could be your raw material, labor, renting, etc. So it depends on the model. But the main idea is that for each one of the variables, you will add a distribution.
Todo, mas a reunião não tô só como ouvinte.
Right? So you will add a distribution, okay? For each one of them, you will add a distribution like this in order to prepare it for the Monte Carlo simulation. Now, the Monte Carlo simulation process is an iterative process, right? Where you set up a number of iterations. For example, 1,000. So this is what's going to happen. You will get and you will fetch one sample, a random sample for each one of the distributions, like this. Let's say that these are costs, right? Cost A, B, and C. So this distribution is going to generate a sample. This sample is going to be included into the model like this. It's going to go to the model itself and it's going to recalculate it like that. And then you will have iteration number one. It's going to be, let's say, 140, say 140 millions. Then I go to iteration number two. Iteration number two, I get and fetch random samples from here. These random samples go to the variable is replaced with this number, go to the model. I do a new calculation, and then with n equals 2, I do, and it says 138. And then I do that for the 1,000 iterations, right? I run this model, and you will see in the tool that it runs for n number of iterations, like this, right? So at the end, I will end up with 1,000 of these, and with all of them, I can generate a graphic, a distribution like that, right? And that's the main idea of the Monte Carlo simulation, right? That you will get all these iterations. These iterations can become a distribution, right? Will become a distribution. And from this distribution, I'm going to show you how to interpret the results, right? Now, please remember, right? Something like this. You have the results, and then you have the distributions. Now, please remember that the y-axis of a distribution is its probability here, and the x-axis is the variable analyzed. It could be cost or it could be time, right? And here is how frequent it is. So if I am here, that means that this range of the variables is more frequent than the blue range, which is here, right? Because you have less probability. These ones, they have the highest probability of occurring. Here you have the lowest probability of occurring, right? Like this. You see? That's the main idea if you're looking at a distribution. The higher the bars is the higher the probability that you get the values inside these ranges, right? The lower the bars, right, is that you have less values in these particular bins, right? That's why you see the distribution like these little bars, because they have bins, right? Now, these are the probabilistic distributions that I already talked about, so I'm going to skip that part, right? Let's see here. And I'm going to stay here because this we haven't seen yet. I explained what a distribution, a probabilistic distribution is. A probabilistic distribution has some parameters, and it could be of two types, right? Discrete, meaning that you can have only round numbers, and these distributions are used to count things. How many times this risk can occur? How many times am I going to have a traffic accident? How many times my security system in the painting structure that I have is going to fail, right? How many times? And then you have a continuous distribution, and the continuous distribution is going to be a continuous range. You can have fractions, you can have decimals. So it is utilized to measure the time, the cost, and any other variable required not to be an integer. Like, for example, the time of the consequence time of let's say of a machine breakdown, the time that you take to ask for a different product, right? And the product comes. In this case, the cost of a penalty that, I don't know, the regulator put into you, etc., etc. So you have a lot of different things that could have time and cost, right? Now, which are the distributions? And I said before, right? You will have a very few. You will have a Bernoulli or a Poisson distribution for the discrete ones. You will have a PERT, a normal, here a uniform distribution to use it, right? So with that, you're done. Now that we know that every distribution has parameters, it could be discrete or continuous, right? Let me go to one topic that it's very, very important. It's called the percentiles, right? And the percentiles are these figures that, and we're going to see a few examples. For example, here, if I say that P90 is this number here, which is April the 9th, 2016, right? April the 9th, 2016, this is P90. That means that you have 10% probability, right? You have 10% probability, right, of finishing the project after this date, and then you have 90% probability of finishing the project before. You have 90% probability of finishing the project before 4/9/2016, like this, right? And then you have 10%, right? You have 10% probability of finishing the project, after 4/9/2016, right? That's what it says. This is how we read it, right? So why is that it's so important to know how to use or how to understand the concepts of percentiles? Because these are going to be, sometimes it depends on the country and the industry, these are already in the contract. So the regulator might say, for this construction project, you have to declare your PAT. So that means that you're going to tell the regulator that you're going to finish February the 29th, right? February the 29th. This is the date that you're going to be, it's going to be your PAT, meaning that you have 20% probability of overpassing that date, and you have 80% probability, right, of finishing it before, right? This is what we're saying here with the percentiles, okay? Now, let's always remember, and before I start, let's always remember that our main objective is to move from a point estimate. Remember, for a static scenario where you have, I don't know, 200 days, $3 million, right? And evolve from a single variable to, in this case, a probabilistic scenario like this. So your point estimate is going to be here, 600 days, and you're going to move to a distribution. So this is what you should expect from your model, right? That your model is going to move from a point estimate to a distribution. Okay, so let me open a model, right? Give me just 1 second. Let me open a model. I'm going to open this tool, which is called Model Risk, which is an outstanding tool, and we're going to use it to run this. Just close this model, no worries. We're going to have a model there. If you want, because I saw one quick comment there in the chat, if you want the examples or the slides, etc., write to my email, right? I will send my email here. It's Gustavo at perryfieldgroup.com. So if you want, I can definitely share that. Happy to share it with you. I can share it in the same folder where I'm going to put the QRA video. Okay, so now let's take a look to this model here. Right, let's start with this simple model what we have here. Right, so this simple model is a cost estimation model, as I said before, and what you have is this, right? You have 7, if I'm not mistaken, you have 7 items, very simple, right? And these 7 items that you have are going to sum up $4.3 million, right? And this will be your static model. Let's say that you have a team of people, the team of people they did some calculations and they came up with these numbers. So that's perfect. Then what you do is you say, well, now let's get to the scenarios. I'm going to, right, to reproduce the history that I've been telling with an example. So you have your optimistic scenario. You see that everything is better than the other. 600 to 300, this, like this, everything is better, right? Everything is green here, right? Everything is really better. And then you have the pessimistic scenario where everything is really wrong, right? You see that instead of the average of the implementation, meaning 2.5 million, it would say 4 million. The testing goes from 600 to 1,000, this from 500 to 800, etc. Right? So that means that the 3 scenarios that the company or your team is analyzing, they come from 2.9 million to 6 million to 9 million. So it's very wide. You see the range of the scenarios that you have is really wide. So normally what you would do, you would ask again. This is how I normally do it, right? Instead of asking people, or maybe for what's the worst potential case and what's the best potential case, what we normally do, we ask it like this, right? We have the items list like this. This is step number 1. Step number 2, you ask for the minimum. Step number 3, you ask for the maximum. And step number 4, you ask for the most likely. Why is that? Why is that, for example, I don't ask for, oh no, design. What's the most likely of design? 500. Because if people say, well, what's the most likely of design? And then you will say 500. And what was going to happen if I ask for the min and max, they will say plus minus 10%, right? Plus minus 20%. So that really invalidates the exercise, because what I want to do, I want to extract the asymmetries that everybody have in their head, right? Because we know that sometimes the team is new, the technology is new, the labor is difficult, that the tasks are not well defined, etc., etc. So we know we have and we have it also in our history, that we have some biases here, and some things are going to go well, and some things are not going to go that well, right? And that's why I wanted to give you that, right? So this is a good practice that what it does, it eliminates what we call the anchoring bias, right? The anchoring bias is this bias where people are going to give you numbers, but these numbers are biased by an anchor, like the 500 plus minus 10, right? That's what we need to understand. The moment that we understand that, it gets really simple, right? So that's an additional tip that I wanted to share with you. I've done this before. Sometimes it's as simple as sending this in an email to all the different phase owners for a project, and you say, well, please take a look here, use the min, the max, and the most likely, fill it like that, and they send it to you in an email, and then you just compile everything together in one sheet and run the simulation, right? So now that we have that, I set up this like that, right? Like this. So you have a minimum, you have a most likely, and a maximum. You see that the ranges, they are not as dramatic as this. You see, this was 3 million to 9 million. But then when you explain what this is going to do, the ranges are now 3.5 to 7 million. You see, we narrow it down a little bit. The complete, of course, the complete range of the project, and of course we have for each one of the elements we have our range, right? So this is the first part of it. Remember to set up a range. Once that we set up a range, we can transform this, and I will do it here, in a distribution. Let me show you how, right? Let's say that we take the implementation one, which is here, the one in yellow. We set up the scale here, and scale here it says that it goes from 1.5 million to 4 million, which is here, 1.5 million to 4 million, with a most likely of 2 million, right? So now that we have that you see here that has a bias, a pessimistic bias here. So this is good because remember that we wanted to have optimistic and pessimistic scenarios. Now through the distributions, you can make each one of the items pessimistic or optimistic, right? Which is great, right? So now you have pessimistic or optimistic like this. What else you have, right? You have a way of generating this as a triangular distribution. It's just a matter of setting it up like this, right? You have the base range between 1.5 and 4 million, and you go like this at the 2 million level, like that. And this is going to generate the distribution. So the main idea is that you will set up a distribution for potentially each and every one of the variables, right? And the bias for each one of them are going to change like this. This is the nice thing about this. This could be in the middle. This could be very optimistic or maybe pessimistic because this is costs, right? Or optimistic if it goes like that, right? Every one of them can have a different distribution. Every distribution can be different. So for example, this could be a triangular distribution, but other can have a PERT distribution, a uniform distribution, a normal distribution. Every one of them can be a different distribution each, right? And that's a nice thing about Monte Carlo simulation that doesn't limit you to use one distribution for all of them. You can have a lot of flexibility there, okay? Now, what is it that you have to do here? You can set up the distributions like this. Let me show it to you here. Here, let me show it to you like this in the model. So let me close here, and I will show it to you everything, right? So right now, what you have is what we call the first part. Let me show you here of this risk frame that I was showing you before. Right? This risk frame, remember, was done of uncertainty and risk events. Remember that we talked about that when we define risks. You have uncertainty, and then you have risk events. And this is what we're going to do now. We're going to set up uncertainty first. Uncertainty, remember, because of the natural oscillation of the variables, where probability is 100%. Right? This is what we're going to set up right now. So I'm going to move here, and I'm going to set up a distributions like this. It's going to take 1 minute. This is not a demo of the software, so I'm just going to be doing one, and then you will see what happens. I'm going to use, I don't know, a PERT distribution. PERT distribution uses 3 parameters. So I select the distribution. Every software that uses Monte Carlo simulation has this, right? Different colors, different palettes, different distributions, but they are going to have most likely the same ones that I have in my most used distribution, like the PERT, triangular, normal, etc. So I'm going to use this one, the PERT distribution, like this. And you see, I have the parameters, minimum, mode, and max. So I will say minimum is going to be 450. You see, mode is going to be 500. and maximum is going to be 700, like this. Now I click insert to worksheet, and what happens is that this is going to start generating the samples. Remember what I said before. I'm pressing F9 in my keyboard, but this is generating the samples. What I can do, as this is an Excel model, and this is normally what happens, I can copy that. And all of them are going to be distributions. All of them are going to change every time that I press F9. This, what it does, it reflects reality, right? In a better way. I'm not saying that this reflects all of reality, no, but in a better way than having a static model. What I can do is I can do a summation of all of this, right? Like that. So I can see what is the level of my model, like that, right? The summation was here. I'm sorry, the summation was here before, right? Like this. So you have this both output, right? And you have this summation here. This output, I'm just saying, as when you define an output, which remember was the last part of my graphic, the output is where you recollect, is your placeholder, your bucket, where you throw all the results from the simulation, right? So now that I have my distributions here that move, I have the model logic, which is the summation, and I have my output, right? I can run a simulation. I can run, I don't know, 5,000 iteration simulation. I'm going to do F9 5,000 automatically. So I run and simulate here, and you're going to have a progress bar like this, right? So what happens in the back, right? Well, while it runs, what happens in the back is that the model is going to be recalculated 5,000 times, right? This model. I have different models here in this sheet, so that's why it's taking so long. I'm going to stop it in a few. When it finishes, and you will see, you will have in this placeholder, which was called total cost, you will have the 5,000 iterations or the, I don't know, 2,000 iterations that I have here, right? That's the main idea of it. So I'm going to stop it, right? Like that. See, and what I'm going to get is this. Let me show it to you. Don't you worry. I'm going to go step by step. So I'm going to have the total cost, and I'm going to look at like this. And this was the first graphic that we saw. Remember? This is the very first graphic that we saw. Let me make it very, very minimalistic. No things, very simple, like this, right? So this is the total cost. And the total cost goes from 3.7 million to 6.1 million. Remember that we had an initial range of 3.4 to 7 million. But after running the simulations, you see that after running like 3,000 simulations, the mean is 3.7 and the maximum is 6 million. You see that you don't get to the extremes, and this is one of the things that you will learn when you run models, right? You don't get to the extremes all the time, right? You set up some potential theoretical streams, but you don't get there. You're mostly here in this area, right? Now, what is the mean of the project? 4.6 million. Remember that the mean that we have, our reference value, was 4.3 million. Now you know that the expected value of the model is already 300,000 more than the original one, right? So that's the second thing, right? That means that, of course, after you interviewed your subject matter experts, what happened is that now you have a much better view of what could happen with your project. Now, third thing, what you can do, you can set up something that is called a marker here. Let me show it to you, a marker, which is 4.3 million, right? Your reference value. This is the third thing that you can get from a histogram, right? So you can come here, you click in OK, and you say that you have 25% probability to get to 4.3 million. This was the original number that you had at the beginning. That means that this 25%, which is here, right? We make it here, more or less, right? 25%, and then you have 75% here. That means that you have, there is 25% probability of finishing the project in less than 4.3 million. This is it. So all this area here is good, right? Is your good area because you finish the project in less than your reference value. But reality hits very hard, right? And then you say, but also you have 75% probability of finishing the project after or in spending more than the reference value. It means that you have in every, if you run the model, 3 out of 4 scenarios are going to be bad for you because you're going to spend more than what you said you were going to spend, right? Now, if you're lucky enough and you don't run the simulation, the Monte Carlo simulation analysis once the project started, which is normally the case, and you're just planning the project, what's going to happen is that if you're in this particular dilemma, right, where you have 75% probability of spending more than what you had, so what you can do is like you can negotiate and say, look, why don't we, right, add another marker, add a marker here that is going to be your PAT. So I want to be safe. My risk appetite is going to be the 80%. I'm going to change the color, maybe make it, I don't know, red here. And let's see, it's the custom marker color is going to be red as well. And I'm going to make it this like that and more weight like this. So this is my PAT, which is going to be there, which is 5 million. So if you're planning the model, what you can say is like, look, the reference value that we have is not going to be built, right? We're not going to achieve it because it's way too low and it's very optimistic. Maybe let's get more realistic and I offer you this model in 5 million. And maybe what the question that you have is like, okay, so you're talking probability. So what's the probability that 5 million are going to give me? And you will say you're getting 80% with that. Before with 4.3 million, you got 20% probability in your favor. But with 80%, if you want 80% in your favor, you have to charge 5 million at least, right? And that would be the reasoning. And that would be the way where you can explain this to people, right? Now, there's one thing more that you can do. I'm going to do something that's called naming the distributions, which is every software has it. So I'm going to name these distributions like this. I'm going to set it up like that and say these are inputs. Don't you worry, because this is about QRA, so don't you worry. I'm just giving them names, right? Like this. I'm going to run the simulation again. This time only 1,000, because I see that the Teams normally slows down things. So I'm going to run this model 1,000 times. Right? And what I'm going to do, I'm going to run what I call a sensitivity analysis. So the sensitivity analysis, what's going to do is going to give me what is the importance, the relative importance of each one of the variables here, right? Like that. So I have this. What I can do is I can do a tornado chart. And I will say, I want the tornado chart for this, right? For all my variables here. I'm going to show it like that. Don't you worry about the operation. It's like, what is the main variable that I have? The implementation pipe. 95% of the risk of my cost model is represented by this, by the implementation pipe. That means if I take care of that and if I mitigate the risk that I have there, I will have a much better result there, okay, in my cost. So this is the first element of my Monte Carlo simulation model, the costs. Now, the second element, remember, is the risk events. And the risk events, they come and they are inherited somehow from the qualitative risk analysis, which is here, where you have all these potential risks like problems with community, resource scarcity, exchange rate exposure, etc. Right? And you will remember that you will have some type of matrix, right? Matrix like this, where you put your risks, let's say here, and let's say that you have your couple of risks are here, there, like that, and this was your visualization of risks, right? So with QRA, you no longer need that, and what you're going to have a tornado chart that's going to tell you, right, what are the main impacts and what is the ranking of your impacts here, right? So what I did, I generated, remember the distribution, the discrete distribution that I told you that I was going to use, which is here. So this is the discrete distribution, and this is the continuous distribution. The discrete distribution is going to count, remember, how many times the risk could occur. So if you take a look here, this portion in yellow, right, is going to tell you how many times the risk can occur, right? Now I move the yellow portion here, and this is going to tell you the total impact of that distribution, right? Why? Because in that case, if you have this distribution here, for example, for the resource scarcity is going to happen once, right? And you have an impact of that. Of course, what I'm missing here is that you will have, and I'm going to make it very simple, right? I will have to multiply, remember, because the risk was the probability times the impact, right? So this is the total risk that I will have. Total risk. So why is that? In this particular case, I have 0 risks. If I do F9 again, 0 risks. But in this case, I have one problem with the community. So I multiply this times that. I have 0 risks. I multiply. I have 2 risks occurring. So I multiply each one. But sometimes I will have 2 risks occurring. Look, 2 resource scarcity issues. And then I have to multiply the impact times 2. Of course, this is the very basic model. You can improve and make it more complete and complex, but I'm taking a lot of licenses here because I want for you to understand what is the real impact of the risks here. You see? So basically, I'm predicting the future, trying to predict the future, how the risks are going to come. You see that at the same time, I am generating the cost and I am generating the risks. So I will have to add a summation here, sum all of this, and convert into an output, right? Because I want to collect all the samples here, right? So this will be total risks, like this, right? Like that. And what I will have to do, I will have to name the variable. So let me add a name like this. I'll add name. So now you see that the methodology is very repetitive, right? It's very mechanical. So you will know how to do it in no time. It's very simple. And then I will run it again. I will run only 500 because of the time. And I'm not sure why is it so slow, but let me run it with 500 only, just because of the time. Right? Now it's working faster. Maybe it was my Outlook. Take a look. It was much faster. And now what I will have here, right? I will have my total cost, but now I have my total risks as well. You see? And I can take a look to my total risks like this. So this is my total risk. This is the potential risk that I will have in my model. If I like, and I have it in here, I will show in a second what happens if I do the summation of the two of them. Now, if I want to see, this is the analysis of only the risk, because sometimes we have people in these trainings where you're only focused on the risk. So here you have, it's a long tail, right? Because you have a lot of potential events with very low probability. Once you have that, right, you can set up a tornado chart for the risks. Remember that you can have a tornado chart for the cost, which is, right, 95% of it is the implementation pipeline. But if you're only focused on the risks, take a look what happens to the risks. You have the two main risks are problem community and resource scarcity. So if you're focused in this particular item, which is the risk register, right, now you know which are the main risks. This is going to replace your risk matrix, right? That's the main idea. And finally, what you can do, you can set up the summation of the two. You see how simple this is. I can set up the summation of this plus this. So every time that I press F9, you see, it's going to change, right? And this is going to be called an output again, grand total, right? It's going to do the summation of the two. I think I already had it, but I just wanted to construct it with you, to build it with you step by step. And I run the model again, you see? So every time that I use or create a new output, this is going to run the model again. I need to run the model again to populate it. And this is the base of Monte Carlo simulation. Populate these samples that are going to give you the total. So you see that now I have this grand total here, and I can go to the histogram and say, look, I want to see my total cost. That's great. Then I have my total risk, which is here. So let's take a look to the grand total, the total cost versus the grand total. Take a look. The total cost at the beginning was the red histogram, was like this. But then when I added the risks, it behaves more like the framework that I show you that goes like that. Let me go back to the framework figure like this, you see? It goes like this. Why? Because you have the risks here and you have the cost there, right? And that's mostly why it happens, right? Because you have the two elements together. Of course, sometimes people don't like, and I'm one of them, I prefer these cumulative curves, and always try to make this as minimalistic as possible. I mean, only show the information that you need, so I don't need the markers anymore, like that, right? So you can see what is the effect from bringing the risks to your model, right? That's what happens when you brought the risks. That's what happened, right? Now, once you have that, you have the ability, now that we have this grand total, you have the ability of checking out the tornado chart, but the tornado chart for the grand total. That means that this is like blending together the cost and the risk register in one risk matrix that is now replaced by a tornado chart like this. So now you see that the main risks are problems with community, resource scarcity, environmental issues, and then you see the real effect of the implementation pipe. So the real effect is very small. We thought at the beginning that it was very big, but then you compare it and you relativize it, and then you see that it's very small, right? So these are the types of things that you can do with a tool that does Monte Carlo simulation. Now, let's go and check out everything that I said is here, right? I don't see it because maybe this is the number 20. This is the number 20, introduction to QRA number 20. So that's why, but you have all the things that I said there. Now, let's take a look to some examples, right? One is the one that I just told you, right? Which is that you have the histogram, right? We understand the different outcomes, and we only compare, we will take into consideration uncertainty. Remember? But you can consider uncertainty and risks. See, when you have this little icon, that means that you have your risks here. And now you know what is a PAT. Now you know the mean, you know the boundaries of the distribution. These are all the things that you didn't have in a static model. You can do an overlay, which is what I just did. When you overlay the cost with the cost plus the risks, and it's actually the framework icon, right? It's actually what you see here, right? You can do like this. You can overlay cumulative distribution functions. How is it that you read it? For example, here you have your P95, right? Your P95 for this distribution is going to be 5. Here, I'm sorry. P95 for this distribution is going to be 5449. P95 for this distribution is going to be 6 million. This is how you read it, right? You see the level here, and then you see it. Or what I can do, I can say, oh, okay, so I have 5 million, and I do it like this, like that, like this. So 5 million is equivalent to maybe 40% in the red curve and 80% in the blue curve, like that. That's how you read it, right? You can read it right down or up left, right? Like that. You have distribution, you have tornado charts that are going to show you which are in here. My requirement is don't see the numbers, see the relative weight of the variable. So the variable, this is telling you that the implementation of pipeline is the biggest one, right? And this is giving you the scope of it, right? But my idea was to show the tornado charts in a way that you know what these are for, but then you can investigate a little bit more. Otherwise, you have many different tornadoes. For example, the tool that I'm using has 8 tornadoes, right? So that's the idea. Now, how is it that you can calculate contingency, right? So we only have like 5 more minutes for this, so don't you worry. I know it's Friday, so thanks again everyone for coming. So how do you calculate contingency? This is a recommendation that that we have. That one is that you have contingency reserves for some risks, and then you have management reserves for unforeseen risks, and then you have the exposure of the project, right? Every company does it differently. Every company, even in the sometimes in same departments in the same company, they do differently. So normally this is how we see it, right? And it depends on the company. Sometimes, and this is what we've seen, is that the difference between the mean and the 80%, they call it contingency. Sometimes, because I totally acknowledge this, sometimes they do this including the reference date or the reference cost. Remember the 4.3 million. So it depends on the company if you want to include the deterministic or the reference one, right? And they call it contingency, right? To PAT. So this is for risks that can occur. So let's imagine that you plan here that the mean is 2.7 million and your P8 is 3 million. That means that you have an 11% of contingency. Right? That means that this is money that you will spend the moment that the risks start to occur. Right? Now, what happens with the managerial reserve of the management reserve? This is for unknown risks. So what happens if things start to go south? And then you have a 3.6 million here in your P95, right? Which is exactly this. Right? So this is the type of money that when risks start to occur, you will knock on the door and say, you know, I need more money for this because the things are not getting very, very promising. So this is the type of things that hopefully the company is going to take. This is not part of the project's budget. This is part of the company's budget, right? That's the second level. And the third level is the exposure. And normally you don't plan for this. And it's the difference between P95 and the maximum, which is basically this. And you don't plan for it. Normally what happens is that this is the risk of doing business. This is the risk of the guy in the rope at the beginning of the presentation. This is it, right? He knows that he will have a risk of losing maybe, I don't know, 1.4 million. If everything goes wrong, right? If there's a pandemic, God forbid, but that's what happens with that. And this is an example of a contingency calculation. Let's talk schedule, and with this we finished, so don't you worry. So first of all, when you do scheduling, instead of having cost items, you have tasks. So these tasks are going to have distributions, the same principle, right? Then you will have a risk register, same components, and that risk register, you will have to map the risks to the tasks, like I'm doing it here, you see? I'm mapping the risks to the tasks. That's the complexity here, right? Because normally in Excel, you do it as one, or perhaps you can add it one by one in the cost items, but normally, as we're talking money, normally this is how you do it, unless you're doing a cash flow, right? Then you run the simulation, and now your interface is going to talk in dates. It's not going to talk in cost. So here you will have the same thing. You'll have a PAT, right? 80% probability that project finishes before, and 20% is going to finish after this. Right? Same thing here. If you have a reference number, which is the 4.3 million, you have here the September number. For example, adding a target value always helps. Why? Because you know that you have 30% probability of finishing before and 70% probability of finishing after that date, right? What else you can do? You can set up in duration. So instead of looking at finish dates, you will set up durations, right? Like that. And you can combine the two, you see? The good thing about this is that when you run a model that has schedule, then you also have the possibility of doing cost, right? So that's the nice thing about this. You can combine the two. You can have schedule and cost in the same time, in the same file even. So that's a nice thing about this. Now, what else you can do? You have tornado charts, as I showed you before. You have tornado charts that are going to share and show the impact that you have for your risks in days and in money. So you see that now you have 2 dimensions when you run it in a calendar. When you're running a cost model, you only have 1 dimension, which is cost. When you run it in a calendar, you have 2 dimensions, which is cost and time, right? That's important for you to know. You can generate scenarios like this. Let me see if I have the graphic here that I wanted to show. If not, it's totally fine. It's totally fine, right? Which is here. No, it is totally fine. I think it was the scenarios one that I have here. Now, just to finalize, please remember that this is not the only step, right? I did this calculation in this model for the first phase, which is the inherent or the pre-mitigation and the current risk phase. But then you will have mitigation actions, and then you will have a copy of this model improved, which is called the residual or the target risk model, right? So remember that always you have this time component, which are the inherent risk, the mitigation, and the residual, or the current, the actions, and the target, or the pre and the post mitigation, right? Depending on how your team is set up, you will run this or not, or people in your team are going to run this or not, right? So always remember that. Now, let me go here in the steps of integrating QRA and the conclusions, right? Now, main steps to integrate QRA into your models. Now that you've seen that this is a sample methodology that I use, that it's, I hope, quite simple and quite straightforward, right? First of all, you add uncertainty to the model, right, which is in the shape of distributions. Then you add your risk event to the model, remember, in the shape of a risk model. And maybe this is part of an additional analysis is to add correlations to the model, right? I'm not going to touch on the correlations, but this is part of it, right? So first you add uncertainty, the risk events, and potentially correlations if you have the information, right? That is always the main idea. So here what I did, I'm not going to go in details into that, is the step-by-step of adding uncertainty to your model. How is it that you need to do it? And of course, you're going to have access to the video as well, right? Now, main tools that you can use for doing that. The tool that I use, it's called Model Risk. It's really nice. It's very versatile. That's the one that we promote here. The one that I use for the schedule is called Safran Risk. It's also an outstanding tool. That's the one that I use for the schedule and risk analysis. There's one, it's called Chance Calc. There's one which is called MC Flow. There's another one called Risk AMP, if I'm not mistaken, right? That can generate the same thing. The methodologies are more or less the same, right? Some of these are paid, some of these have free versions, some of these are more like, there's another one, it's called Yasai. I'm sorry, like this, blue, here you go. It's called Yasai. It's totally free, but it doesn't have an interface. So it's for investigation, for research purposes only, but it's good if you like to start. Model Risk also has a basic trial version that lasts for 15 days, and then you have a limited version for a year, I guess. So it's up to you from which one you start. I think that the main message here is for you, please start, please do start, right? That's how we see it, right? Main conclusions from what I've seen, and hopefully you share that with me, that QRA is simple. I mean, you just have to replace variables with distributions. Can be utilized for many applications: cost, scheduling, project analysis, etc. Probabilistic analysis improve the decision making. You see that now that we have a probabilities on the table, we have a much better discussion. We raise the level of the discussion and can be implemented using all these different tools that I show you, right? So my recommendation is take one of these tools, write to me, please write to me, because I'm going to share the video and the material. But if you have any potential or any, I don't know, any question or anything like that, please feel free to write. I'm not going to answer, I don't know, the very same day, but of course I will answer during the week. And the main idea here is that why is it that we do that? Remember, the why that we started this with at the beginning is, why is it that we take this all into account? Why do we bother? Right? It's because we have to improve our decision-making process. we have to stop. I mean, we have to add, and this is my recommendation, right? Add some scientific base and support to your decision making, right? Otherwise, you're going to do decision making only based on your hunch or the average, and you have very cheap tools. Some of them are even for free that are going to let you add probabilities to your model. And this is not difficult. You see that we've created a very complicated model in less than an hour. So it's not difficult. And if you have questions, if you need help, of course, we're here. You can contact Jameson. I'm not sure if Dan is here, but you can contact them. And the main idea is for us to handhold you and get into this world of probabilistic risk analysis. That's what we like. That's what we do. And try to define always ranges, quantify the outcomes, and of course, try to make an informed decision at this point.